Hello, Nancy.
Hi, Shane.
So today we are talking about the ozone hole.
Yes. Do you remember the ozone hole?
I mean, I know what it is.
But you don't remember
Do you actually know
the-
when, what the timeline was for it? We were talking about this beforehand.
Yeah, like in the mid-'80s is when they kind of first, I think, discovered
I was born
there was the ozone hole.
in the mid-'80s.
Oh, God.
I'm assuming you remember.
I do remember. Oh, I'm assuming because you're so old. I'm not that old. But I do remember the ozone hole. I remember because I was a kid. I was, like 8, 10, whatever. I remember it was such a big deal. Hairspray.
Oh, sure.
Because hairspray had the stuff in it that that was bad for the ozone hole. So people were like crazy about not using hairspray.
Well,
and
couldn't you
bug
just use
spray.
couldn't you just use like a pump?
Well, they didn't have it. No, that's the whole point. That didn't exist, Shane.
Well, don't look at me like that. I don't know.
It was like those aerosol cans
Yeah,
that
sure,
no one
sure.
uses now, or they use it now, but with different propellants or whatever it was. But it was like that was what things were. And I remember it was like such a big deal.
That's funny. I had no idea that. I mean, that totally makes sense.
You
but
shun them, you know.
Now I just think of for me, the thing I think about is when I go to I get takeout somewhere, and a lot of places are really good about this, and there's a bunch of laws and everything, but there's still food trucks and things where you get styrofoam.
Right.
I just know there's
so
something
bad.
it's just bad. I just can't. Oh, but I don't necessarily have to worry about hairspray. I put a lot of stuff in my hair. There's no hairspray. Welcome to the American Geophysical Union's podcast about the scientists and the methods behind the science. These are the stories you won't read in the manuscript or hear in a lecture. I'm Shane Hanlon. And
I'm Nancy Bompey.
And this is Third Pod from the Sun, Centennial Edition. Okay, so we're not here today to talk about hairspray. Unfortunately not, no. What are we talking about?
So this is one of our Centennial episodes, and this month for the Centennial, we're focused on or looking at atmospheric science. And one of, the biggest kind of scientific, I guess, problems that we faced relatively recently, and that scientists
more recently for some of us.
that scientists kind of figured out what to do about it was the ozone hole. So it's actually kind of a great success story, really. And there's things we can learn about it. So, Janessa Duncombe, who is a intern in EOS, our news website, and I went up to NASA Goddard a couple weeks ago and talked to two scientists there who've been involved with figuring out what was wrong with the ozone hole, and then now a lot about the recovery of the ozone hole. So, hi, Janessa.
Hey, Nancy.
How's it going?
Oh, it's great. Yeah.
I have to say right now, it's snowing outside in mid-November, and it makes me so very happy.
Yes, I know.
Gorgeous.
So tell us a little bit about, you were there, we went up there together. So you were not bored when this whole ozone hole thing was going on.
Oh, no. I was not even on this planet. I'm a 90s baby, okay?
Wow.
Proud. I am proud. So we went up to Goddard, and I was really curious to learn about it and hear these scientists talk about what ozone really is. From what I learned talking to them, it seems like ozone is this protective shield that goes around the entire Earth, and it keeps us from harm from the ultraviolet rays that come from the sun. Those can cause, skin cancer, cataract, damage plants, and everything. And some things that humans were putting out with hairspray, Nancy, and other things.
Refrigerators, air conditioners.
Yeah. Right.
Yeah.
There was more than just the hairspray. Okay, more than just the hairspray. But those were starting to damage ozone and cause a thinning of our protective layer. And it seems like it was actually a really scary time for a lot of people.
Yeah, it was. So now we'll hear from Susan Strawn and Ann Douglas a little bit about the ozone hole.
I'm Susan Strawn, and I'm a senior research scientist here. I've been at Goddard for 26 years, but mostly working on the ozone layer and stratospheric chemistry and dynamics the entire time.
My name is Ann Douglas. I am also a senior researcher at Goddard. I have been here in one way or another since 1981, which feels like forever. And I was project scientist for the Aura satellite and I was co-lead for our chemistry climate model. And I've been working on ozone and satellite data and all sorts of questions about what will affect ozone my whole career.
And so the first published report of there being something unusual about Antarctic ozone goes back to 1985, a paper by Joe Farman and others. And they had been looking at October levels of total column ozone at Halley Bay Station, which is pretty high southern latitude. And it had been at some value, throughout the 60s and early 70s, somewhere around 300 Dobson units. And then they noticed starting the late 70s, early 80s, that value was declining, and pretty rapidly. And that decline was greater than the sort of year-to-year bouncing up and down that you might expect from just meteorological variations. And so that was the first publication that alerted people to there being something strange going on over Antarctica.
As soon as it was reported and people realized they could believe the instruments, then you had from the satellite data not just a single point, but you had a
You had a map.
You had a map so
big
that you
map.
could see what was happening over this larger geographical area, and then you could also see, when you look back now, you could see how it had been developing between 1979 and 1985, 1986.
So if you went back and actually looked at that data and you could see it now that.
Right, you would have a whole, like she said, a large geographical map of the whole southern hemisphere, and you could see that it was like a little bit low in '79, the first year they had measurements, and then it got lower real fast. In 5, 6, 7 years, it was now getting really low.
But it also bounced, and that's why it took a while for there to be a good theory.
So when it first came out, though, that they saw this decline in ozone, were people guessing like this could be it, or how did? I mean, they didn't know what the reason was, right? They didn't.
Farman actually had a plot showing CFCs going up, and he's like, I think that could be the cause. Mm-hmm. It showed ozone going down and chlorofluorocarbons going up, and so the decline was definitely correlated with the rise in chlorofluorocarbons, but as you know, correlation is not causality. Mm-hmm. And so people needed to understand what was happening. And so the other thing, of course, is that chlorofluorocarbons themselves, they don't affect ozone or anything else. They're wonderful inert molecules, and that's why we use them in so many ways. You can breathe them, they don't hurt you. You get them on your skin, you don't get a rash. Mm-hmm. They're wonderful molecules with all kinds of wonderful uses. Except that if they get above the ozone layer, really they have to get above the ozone layer because the ozone layer protects them from being destroyed, just the way it protects us. They have to get up where they can be hit by ultraviolet radiation. So, not only is, chlorine is going up okay, but then you have to show that the product gases of chlorofluorocarbon destruction, that's what's showing up in the Antarctic vortex. And since they only get destroyed high up, you had to have that, or mostly get destroyed high up, you have that high up air that had to be transported and then come all the way down. Right. And then, so you need this, what we call isolated unmixed descent. And then you still didn't have any chemical processes that would make ozone go down. We had to come up with a whole different set of chemical reactions.
Right. This was what was missing back then. No one expected this to happen. No one had this in their model that there should be this huge depletion. This was really a huge surprise. And it was this was the missing piece of the puzzle, was the ice particles that form in the Antarctic stratosphere. Right, but it turns out there was chemical reactions going on the surfaces of the ice particles, and that was what was missing, but people hadn't thought about for chemical models. And they started putting in some reactions that might go on ice particle surfaces, and those reactions freed up the chlorine from a pretty safe species. So after Anne was saying how the CFCs have to get up high to break down, they do, but they break down into HCl, hydrochloric acid, and chlorine nitrate, and both of those are pretty non-reactive gases, so they don't destroy ozone either. So the key was that in the Antarctic lower stratosphere, on the surfaces of these little ice particles, these forms of chlorine that were kind of safe, these reservoir gases, would get on the surface and react, and they would free chlorine into a reactive form that could then attack ozone. So that's why this big ozone depletion is unique to the polar regions, and it's especially a big deal in the Antarctic because it's so cold there. So you can make a lot of the ice particles, and then you have this processing of the nice safe forms of chlorine into reactive, dangerous forms. And then when the sun comes back, which the sun starts to return to the polar region in August, and then fully sunlit in September, then these reactions go like crazy, and you destroy a lot of
And
ozone.
there's nothing to stop them. There's nothing to slow them down or put on the brakes.
So they're talking about like these reactions and how big of a deal, but like honestly, like how big of a deal was it? Like what's the science here?
Well, what I was reading about these, chlorine, once they're dangerous in the stratosphere and taking out all these ozone, is one chlorine can actually just take out 1,000 ozone in one fell swoop. So it's this continuing reaction that it really has a huge impact.
And the interesting thing was that they told us too was like they didn't even know that like this reaction happened. They didn't know the chemistry of it. They didn't know the physical mechanism of it. So like you're basically, this was all brand new.
Right. So a big deal.
There was furious activity in physical chemistry labs, people trying to measure reaction rates. So that was all going on at the same time. So you had people working with satellite data, you had people trying to model and get quantitative agreement with measurements, you had ground-based measurements, you had aircraft measurements, and you had really captured the imagination of hundreds, if not 1,000 or more.
Oh, yeah.
People. But I think that the ozone hole, when you think about it, all the different things that had to come together to really get the theory, there was plenty of room for all kinds of people who have a diversity of thought and, bring different skills to the mix of what was needed.
And it made the science team meetings really interesting.
Well, it was exciting. It was exciting. It was exciting to go to the meetings. It was exciting when you developed a new insight and you could share it with people.
And it was exciting to be in the field because when we got down to Punta Arenas, where our mission was based, which is down the tip of South America, we didn't know what the answer was going to be. And the airplane would go up about every 3 days, and then you would come down and you would download your data and print out, the time series plots of your species, and then we'd all post our results on the bulletin board and have science team meetings and talk about it, and then it was great because like the smoking gun data, we saw it there in the field. It was a super exciting time. Ozone looked normal and CLO, chlorine monoxide, was low. And then a few weeks later, CLO got really high and the ozone went down. It was like, there you go. It was a really exciting time. And it was also exciting during this mission. There was a lot of the political side of this, the negotiation for the treaty, the Montreal Protocol.
I think we should all be aware of the size of the challenge we are faced with. If we are able to agree, this would be the first international legal instrument reducing substances detrimental to the environment in a quantifiable measure and on a global scale.
That was already going on. But the Montreal Protocol was signed, I believe, during this mission. And it wasn't because of our results. There was other evidence and other reasons to sign the treaty, but that made it extra exciting too. And I think during this meeting, I guess DuPont, who makes the CFCs, they're like, yeah, it's our stuff. Yeah, it's the CFCs. So things happened really fast. 1987 was a very action-packed year.
But when we did get the data, we had a little press conference, and I was young and foolish, and people kept asking me questions, and they'd say, well, this is really interesting what your data says, but there's a volcano, Mount Erebus, down there, and couldn't that chlorine come from Mount Erebus? And then we would explain again why we knew the chlorine wasn't coming from that volcano, that it had to be coming from above. And they said, that's really interesting. And then they go, but are you sure it's not a volcano? And I'm like, gosh darn it. And eventually I lost all my patience, and I was like, Khrushchev, I banged my hand on the table. And I said, we've got this nailed. And when I said this, everyone laughed. And the project manager from NASA headquarters said to me, how does it feel to be a media star? And I'm like, what? And he says, you gave them the quote they wanted. Oh my gosh, it was in the headlines everywhere.
What I would give to be a fly on the wall in that room.
I know, it must have been amazing. Anne was pretty, Anne was kind of embarrassed about it, but I thought it was pretty awesome.
Yeah, that was funny.
Yeah, but this had some serious implications, right? Like more than just like being a big her being a big media thing.
Yeah, I mean this research into the ozone hole and what was causing it. I mean, people got really serious about it. Every country, I think, in the world signed on to the Montreal Protocol in the 80s, effectively banning these chemicals. And we're seeing now the effects of that it is working. The banning of it really led to its recovery and a real success story.
But when you think about it, I mean, like, this is one of the first big problems where we had absolutely conclusive proof that mankind was affecting the planet on a global scale, that what I do in the northern hemisphere, in the United States, is actually affecting the whole globe. Not just my little area. I knew someone who had a leak in their air conditioner, and they said, well, I'm affecting the ozone around my house. And I'm like, well, really not so much. Actually, you're affecting the ozone over the whole world. Yeah. And that, the more that we learned about it, so then biologists and health people and people who worry about crop yields and animals, all of those people are jumping in and having something to say about this. And that a big change in the amount of UV reaching the surface. So like over the ozone hole, now you've got a big perturbation, not a small perturbation. And so, people could see the difference in like the plankton that are down there. So you could really see the impact that people made. And then that really is the fact that we had this global impact is what stands behind the Montreal Protocol and its amendments, and the fact that all of the nations of the world, all of them,
it's amazing.
All of them are signatories
to the protocol and its
and its amendments, and that's just really amazing. And for those of us, the chlorofluorocarbons are also greenhouse gases. They also cause global warming, and so by banning them, we did a solid, we did for global warming, but also the protocol gives us a lot of hope that we were able to create an environmental treaty.
Yeah, so I mean, Janessa, what we learned up there, so Susan and Anne have been now working on this for, most of their careers. And then they are involved today to look at the recovery, right?
Yeah, they're still actively watching the ozone over the Antarctic. So they look at it from satellites, and it's still a really active area of research, honestly.
Yeah, and so they know it's recovering. It's going to take a while, but it's recovering. But I think, remember when we were in the car on the way home, Susan drove us to the metro, and she had a really good analogy. She said she likes to use the analogy, it's like a swimming pool, and it's draining by this little drain at the bottom of the swimming pool. In terms of the recovery, to get all that, if you can think of it, when it's empty, it would be recovered. But there are kids jumping in the pool all the time, so it's really hard to see what the level is. But over time, of course, it's going to drain and it's going to be recovered.
Yeah, trying to see that process is difficult. But
the size of the ozone hole, the area over which you have that very low ozone, is smaller this year than it would have been if chlorine was as high as it used to be.
Right.
So, okay, we're making progress, but everybody needs to calm down because these are 100-year lived molecules.
Right.
So as much as we would like to say, okay, we've done everything that we can do. So we've done everything that we can do, and the problem is solved.
We just have to be patient now.
But now we have to be patient because this signature of, you can think of it as like a sort of like a beacon of a prior folly. It's going to be with us for a really long time.
Right. And so year to year, the thing that determines how big or how small the ozone hole is the temperature. Anne talked about the ice particles and how important they are. If you have a really cold year in the Antarctic stratosphere, well, you have more ice and you're going to have more depletion. So this year is a good example of a really cold year, a lot of the ice particles, big ozone hole. But last year it was pretty warm and we didn't have much depletion. So I've said before, it's going to be a bumpy road. Okay, it's going down, but some years we're going to hit a bump and the ozone hole is going to be big again, like this year. But overall, the chlorine's going down. It's going down very slowly. So if you all be patient till about 2040 or so, by 2040, the ozone holes by then are all going to be smaller than they are today. It'll be, down another notch, a big notch where you can say, oh yeah, it's definitely smaller every year than it was back in the first decade of the century. But it's going to take decades before that really clear signature of recovery is there.
I mean, I think you touched on this a little bit, but what can we kind of learn from that, from this whole story, this ozone story, the Montreal Protocol?
That global problems can be solved. They can be. I mean, I love to explain this to people who aren't scientists or aren't involved in earth science, people that think, wow, climate change is a really tough thing to tackle, which it is. But the Montreal Protocol and its amendments, the success of that international treaty in solving a global problem, something that is an existential threat to all life on Earth, it's working. It's working. So have hope. It's possible to solve big problems. So I think that's the biggest message that I've sort of learned, and that's the most optimistic message that I have from what I've learned in my career.
It's really great to hear about like the science they were doing and how everything they did affected, like it was such a broad area of science. But I'm really interested in them and kind of what it was like for them in the field.
It's been really exciting. I mean, for me, I came out of grad school right at the time when this stuff was discovered, which was good because there's also then funding to do this work. But it was really exciting to go into a field that was kind of wide open. It's like, what's going on? We figure it out. What are we going to do about it? How do we increase our understanding of the atmosphere? So it's been exciting and rewarding, and we learn things that we think really are relevant, societally relevant. So that's continued to be rewarding, and I'm sure that's why many of us just don't ever want to retire, because it's an exciting field to be in.
John Kennedy, when he was inaugurated, he said,
"Ask not what your country can do for you. Ask what you can do for your country."
And I'm not going to lie, I took it to heart. And I think a lot of people in my generation took it to heart. Right. And so when you're making your career choice, we were looking for something that was going to be for the greater good. It sounds so corny. We wanted to work for the greater good.
Yeah, and although I was too young to hear John Kennedy say that live, I'm about half a generation back from Ann, I did grow up in the era where environmental was this really big movement, environmentalism. And so that had a big influence on me as well. And I always wanted to do something with the environment, but I wasn't sure what, and I just kind of was plodding along following science interests until my science interests one day overlapped with environmental opportunities.
So then how did it feel, I mean, working on this problem, this ozone problem, and then to see you talked a little bit about the Montreal Protocol, but when it got signed and then the amendments, I mean, to think that you had a hand in it, a part of it.
It's thrilling.
It's thrilling.
Yeah.
It's thrilling. And all of my kids, and I have 12 grandchildren, 4 of them are quadruplets, which is why they just bumped up in a big hurry. But all my kids and grandkids know that they're supposed to be checking, because the ozone hole is probably going to last longer than
you and I will.
We will. But my kids know that they know that from an environmental point of view, I want them to notice when it's gone, and I want them to tell everyone. My mother was part of that.
Yeah.
It's, like, yes.
And that grandma was right.
And grandma was right. Yeah, that's
Yeah.
She was right.
She was right. That's true.
I think that's just a good place to end it.
I agree.
Yeah. All right. So that's all from Third Pod from the Sun.
Thanks, Janessa, for helping me out with this story. And of course, to Susan and Ann for sharing their work with us.
And the podcast is also produced with help from Josh Spicer, Olivia Ambrosio, Katie Rundell, and Liza Lester. And thanks to Kayla Surrey for producing the episode.
We would love to hear your thoughts on our podcast, on this episode. Please rate and review us on Apple Podcasts. Listen to us wherever you get your podcasts. And of course, thirdpodfromthesun.com.
Thanks all, and we'll see you next time.